Alright, so continuing with the alternating series test exercises, let's go over letter C. Sigma k equals 1 to infinity, negative 1 to the k of ln of k over k. So number one, let's check the first two conditions to determine whether the alternating series converges. So that's the first condition, that the limit b sub n approaches infinity has to be 0. Let's see if it is the case. So limit ln of k over k as k approaches infinity. Well, on the one hand, it turns out that this one is an indeterminate form because we are going to have infinity over infinity, all right, which means that we need to do the L'Hopital's rule. All right, so that's a limit k approaches infinity, ln of k. Okay, so we need to find the derivative of the numerator, which is 1 over k, and the derivative of the denominator, which is the derivative of k, which happens to be 1. In this case, this reduces to the following limit: 1 over k simply as k approaches infinity, and this happens to be 0, which the first condition has been met. For the second condition, we need to show that the sequence is non-increasing, that is b sub n plus 1 less than or equal b sub n. Alright, so in this case, what we need to do, okay, let's ln of k plus 1. In this case, I know we usually use the letter n, but in this case, for this particular exercise, we're using k plus 1 less than or equal ln of k over k. Well, in this case, this inequality is true, so both conditions are satisfied for this for the alternating series test. So now what we need to do is do the second step, which is to find the absolute value of the series, that is sigma okay, no, that's not k equals 1 to infinity of the absolute value of negative 1 to the k ln of k over k. That's sigma k equals 1 to infinity ln of k over k. All right, and well, in this case, we need to find the most suitable test to determine the convergence or divergence for this series. Well, so there's a couple of ways that we can go about this one. Well, I mean, we could, okay, can we do maybe the n-term test for divergence? Well, that is find the limit, but we already did that limit and we got a 0, so that's going to be inconclusive. So no, we will have to think of a different test in this case. All right. How about, well, the integral test? Well, the integral test might work, or maybe, yes, maybe the integral test, or even better, yes, instead of what, because the integral test can be a little bit, you know, a little bit long, and yeah, and the good thing, we already checked for decreasing on the, which is the second condition for the alternating series test. So, well, how about in this case, instead of using the integral test, let's compare with sigma k equals 1 to infinity of 1 over k, for which we know this is a divergent p series with p equals to 1. All right, so it's a divergent p series. So for divergence, then we will have to show that huge is greater than or equal to big. All right, and in this case, well, huge, which is our original problem, let's see if that's true. So it's huge, which is the ln of k over k. Is that greater than or equal to the one we compared that with? Well, of course, it turns out it is, because 1 will always remain 1, but for k in this case, for k really big, ln of really big, that's ln of infinity, that's going to go to infinity, and this is true. So backtracking this to the original problem, well, this whole new series will do whatever the one we compare it with, because in this case we were able to show that huge is greater than big. Alright, for this reason, because of divergence, going back to the original series, then we're going to have that the series converges conditionally. Alright, conditionally in this case. Let's do one more. So letter D. Sigma n equals 1 to infinity, negative 1 to the n plus 1 over 2 to the n. Alright, so number one, we need to check the first two conditions. That is, first condition, that the limit, in this case, n approaches infinity of 1 over 2 to the n. So that is everything except the alternating factor, and this one, well, of course, happens to be 0. Alright, and then so for the second condition, we need to show that this is non-increasing. That is 1 over 2 to the n plus 1 less than or equal to 1 over 2 to the n, and in this case, well, this happens to be true as well, because, well, in the denominator of the left hand side of the inequality, we have this n plus 1 power, making that denominator a larger value than that on the right hand side of the inequality. So now let's take the absolute value of the alternating series and create a whole new problem. And well, this is n equals 1 to infinity. Get rid of the alternating factor to get rid of also the absolute value bars. So that's going to leave us with a 1 over 2 to the n in the denominator, which is the same as saying n equals 1 to infinity, 1/2 to the n power. And we know that this is a convergent geometric series. Alright, and because this series, the series of the absolute value converges, well, then the series, the original series, converges absolutely. Alright, and let's do one more. Sigma k equals 1 to infinity of sine of k over k cubed. Alright, so let's have a look at this one, number one. So on the one hand, okay, so the first condition, limit sine k approaches infinity over, or rather over k cubed. Okay, so in this case, what's going to happen? Well, so in this case, notice this sign. All right, notice sine k, it's actually bounded between -1 and 1. So for large values, you know, this function oscillates between -1 and 1. So it's never going to be anything bigger than 1. However, the denominator k cubed is going to get really big for large values of k, namely k equals infinity. So in this case, here we can clearly see that the limit is going to go to 0, and that's the first condition satisfied. The second condition, the non-increasing part. So that is sine of k plus 1 over k plus 1 cubed, or that less than or equal sine k over k cubed. And well, this one is clearly true because of the larger denominator on the left hand side of the inequality. See how this k plus 1 will produce a larger number than k. Alright, so both conditions are satisfied, the series converges. So now let's check for absolute convergence. Now, how are we going to treat this sine k factor? And we already did something a bit similar when at the beginning of this section. Well, so in this case, well, let's just treat let's just treat this like k equals 1 for now. Absolute value of sine of k, let's just treat it like this, and k cubed. Alright, so, and it doesn't matter because, well, sine ultimately will be 1 all the time, as high as 1. Alright, and well, so maximum attained is 1. Alright, so in this case we're going to use comparison, and I'm going to compare this one with the following: sigma k equals 1 to infinity of 1 over k cubed. And we can do the direct comparison again. No need to do the limit comparison. Actually, I don't think it's going to be a good idea to do the limit comparison. It's gonna get weird, trust me. So in fact, I don't think it's gonna work. So well, let's see. So because of what do we know in this case for about this series? This is a convergent P series. Alright, so because of convergence, now we need to show that tiny is less than or equal to small. Alright, that means in this case that the tiny, which is our problem, absolute value of sine of k over k cubed, is that less than or equal to 1 over k cubed? Well, yes, this is less than or equal because in the case in which sine is below 1, well, of course, that meets the condition that is less than. But in the case in which sine attains its maximum, which is 1, that's when it's also equal. So in this case, tiny less than or equal, which is in this case is true. So in this case, because we obtain a new series that converges, well, then our original series, this one, the alternating series, converges absolutely as well. All right.